Let's have a look at a worked example of changing acceleration during launch using momentum analysis. And the idea of impulse is force times time. So here's the force times time data from our rocket. It's a nice big spike at the start to get it off the launch pad, and then this nice period of time of a reasonably constant force acting on it. Well, if impulse is force times time, then that's going to be the area under this curve. So let's have a go at estimating that area under the curve. Let's approximate this as around about a rectangle, and therefore we're trying to work out the area of the rectangle, and that's around about 0.8 of a second along the base, and around about 6 newtons here at its height, which is impulse equals force times time, which is 6 newtons times 0.8 of a second, which is 4.8 newton seconds. That's the impulse, or the change in momentum of the rocket. So impulse equals the change in momentum, which is 4.8 newton seconds, and that actually equals the mass outside the final minus initial velocity. But of course u is 0 because it's sitting on the launch pad not going anywhere. So that's mv, that's our impulse. Therefore our velocity is going to be our impulse divided by our mass, which is 4.8, and on average our rockets were around about 56 grams in mass. Of course the mass went down as the rocket fuel was burnt and pushed out through the exhaust as exhaust gases, but on average it's something like around about that. Well, let's just grab our calculator there and work that out. So 4.8 newton seconds divided by 0.056 gives us a speed of around about 86. So this is around about 86 meters per second. And if we want to know what that is in kilometers an hour, we can multiply it by 3.6, but it's around about 310 kilometers an hour. That thing was really flying. Of course, this calculation doesn't include drag, which would have reduced that top speed a little bit, but the thing was absolutely flying as it went from our launch pad.